Thank you for joining me today. I'm Lonnie Chrisman with Lumina Decision Systems, and today I'll be demonstrating the use of an AI assistant to collaboratively build a risk management model. Today I focus exclusively on the model-based decision-making paradigm, in which you build computational decision models to inform and improve your decision-making and to manage risks. It's an especially powerful paradigm when you're doing strategic planning, dealing with a novel situation that lacks historical precedent, or have multiple stakeholders with different advocacy positions. My topic for today's talk is how AI assistants can and will help us with model-based approaches, and conversely, how explicit decision models complement current and future AI capabilities. When using model-based decision-making, you start out with a complex, messy, poorly understood real-world situation. You form a conceptual model of what you're dealing with, and from this you build a computational model. And that forces you to define things clearly, quantify the trade-offs, and identify key uncertainties. It's important to keep in mind that a model is, by definition, a simplification of a more complex system. By capturing the key elements and not every low-level detail, it helps you gain insights and obtain a greater level of understanding. Model building is an iterative process in which you progressively refine and expand the model until you're at a point where you can merge the insights you get from the model with things that aren't included in the model to arrive at the point where you make a decision. AI assistants already show promise for helping us with all 7 steps on this diagram. My emphasis today will be mostly on the understand, build, and refine steps. Clearly, if an AI assistant can reduce the specialized expertise that you need to have to build a model, it'll bring model-based decision-making within reach of many more people. Today, I'm not going to talk about mythical AI technologies in the abstract. Instead, I'm going to show you Assista in action with a live demo, and you can come to your own conclusions about whether or how this technology will change the way people do things based on what you see. Assista is an AI assistant that I built for Analytica. If you're not already familiar with Analytica, it's my company's flagship product for building and using visual decision models, and you should check it out at analytica.com. You'll see Analytica today, but it isn't the focus for this talk, and I'm not going to be explaining it. Instead, today Assista is the star. So how does Assista assist you? Well, my scope for Assista is large. It's there to help you use the software. For example, you can ask it, how would I change the color of a node? And it'll provide instructions. Or you can have it do it for you. Assista, change the color of this node to blue. You can ask it to explain conceptual topics or to give you help on Analytica function usage or other features. It can help you locate information within Analytica's extensive documentation. And you can see many other capabilities. The capability I'm most focused on today is creative formulation, which is figuring out how to capture the essence of a complex real-world decision problem in a formal model, in my case as an influence diagram model. Creative formulation is a difficult skill for people to master, but as I hope you can see, it's something that AI assistants seem to be pretty good at least sometimes. For the demo, I'm going to use a fictional example of a proposed lithium mining venture in central Nevada. Now, if you're not into mining, that's okay. This is really about technology adoption, and you probably see a lot of similarities to many other areas. Central Nevada is composed of valleys called basins that water flows into but cannot exit from. As the water seeps into the ground and evaporates, salts and elements like lithium accumulate in these basins over time, mostly in the form of brines beneath the surface. The classic technique for mining lithium from brines requires a huge amount of water, which is an extremely scarce commodity in the Nevada desert. So our mining venture will rely on rapidly developing, cutting-edge, direct lithium extraction technologies. By the way, this will be the first time that I'm doing a live demo with Assista during a presentation, and I don't know exactly what we're going to see since Assista's responses are not deterministic. If I were to repeat the demo, it might go in a different direction with a different set of surprises. So this should be as interesting for me as I hope it is for you. And now I'll switch over to Analytica. I have started up Analytica with a new blank model. The only thing I've done is I've typed the description and the title for this model. And and this is a description that can help us as humans, but also Assista will read this, and it will help it to know what it's working on. So I wrote, we plan to open a new lithium mine in the remote railroad valley of central Nevada, which is Nye County, 60 miles west of Ely. The mine will extract lithium, a significant resource critical for electric vehicle batteries and renewable energy storage, from the lithium brine deposits found there. The operation aims to supply the growing demand for lithium while minimizing environmental impacts. The region faces severe water scarcity, which excludes the use of classical evaporative extraction techniques. Hence, the effort will utilize emerging direct lithium extraction, or DLE, technologies. These technologies are an active area of research and are expected to improve fairly rapidly and continuously after the mine opens. The purpose of this model is to help with the strategic decisions regarding how to scale operations over time, balancing the risk of overinvesting in technologies that will become obsolete with the economies of scale. All right? So, now what we do from here is we will draw an influence diagram. This is the normal procedure, usually starting with objectives. Okay, so often an objective might be profit, for example, and figuring out what our decision variables will be. And these different node shapes kind of correspond to the different types of variables. We'll try to find some variables in between that kind of connect the decisions to the variables. Okay, so I'm not naming these, but we have to figure out what variables to use to represent our real-world problem as a model. And every once in a while, we'll have chance variables. These are uncertainties that have to be estimated, and they will figure in. And sometimes we'll have indexes, okay, which are dimensions of the model. Okay, so now I'm going to delete these, and figuring out how to capture the essence of your problem in a simplified model is tough. That is where the real expertise and challenge of modeling really comes in. So I opened Assista, and I'm going to see if it can help us. So let's see, I'm just going to say I can use your help to figure out how to structure the initial influence diagram, and let's see what it says. Okay. So it's thinking about it. It says, this is a complex problem with many factors to consider. To get started, I recommend you begin with a simple influence diagram for a small part of the total problem. Later, you can progressively add in other factors, but do so only after you get your simple model to compute results. Do you have any thoughts about what part of the problem you would like to start with? For example, one option would be to limit the initial model to a single initial DLE technology and a single decision variable to capture the scale of the operation. You could focus initially on the single objective of monthly profit based only on that initial technology. Okay, so that's a really good suggestion. Start simple, get just a small part of the problem working first. And I think it made a great suggestion there. So I'm going to say your suggestion sounds great. Your suggestions sound great. The only thing is I think that monthly profit, we should do annual. So okay, let's see what it comes up with. Now, as it's thinking, watch the diagram. So Assista not only can respond to prompts, but it can take actions as well. Okay, so some nodes and some arrows just appeared. Okay, it's scrolling. I'm kind of waiting for it to finish before I try to read its response. Added a few more variables and arrows. Okay, so let's see, it's not quite done. Okay, so it finished. It wrote quite a bit of stuff. I'm going to scroll up here to see all the stuff it wrote. Great, I'll get started on creating the initial influence diagram for the model. Here's what I'll do. Create some key variables and decision nodes. Make sure each of these variables has appropriate titles, descriptions, and units. Add the necessary dependency arrows to form the initial influence structure. Ensure that the descriptions and definitions are clear and accurate. Look at the nodes right now. They're all cross-hatched. That is Analytica's way of showing us that they haven't been defined yet. And generally, when you draw the influence diagram, you don't actually define them yet. You're just trying to figure out what variables to use. So the fact that it hasn't defined them is good. But it said kind of mentioned that it made it sound like it was going to define them. I'll start by setting up some variables related to expenses and revenue. Let's begin with expenses. So it says the objective is profit, decision is ore processing capacity in MT per year. Okay, and added some arrows. And then it created some variables for revenue, starting with lithium produced, added some arrows, and then it says, said, let me create the variables and add the arrows now. And then it said, I have created the variables related to expenses and added the appropriate dependency arrows. Now I'll proceed to create variables related to revenue and add the corresponding dependency arrows. Okay. Let me create these variables and add the arrows now. The initial or influence diagram is now created with the key variables, their dependencies, and their proper descriptions. The diagram includes variables related to both expenses and revenue and connects them to the main objective of annual profit. The next step is for you to review and refine this initial influence diagram and fill in the definitions. Once you are ready and satisfied with the initial structure, we can proceed to populate the definitions for these variables, assuming a low-scale mining operation. Let me know when you're ready to proceed or if you have any additional questions on the current setup. Okay, so that sounds good. Now, I don't have it laying out the nodes in a nice sort of easy to look at way. So what we're going to do is we have to rearrange these nodes ourselves. So I usually put objectives on the left, I put decisions on the right, and now you just kind of try to untangle the arrows a little. Okay, so and I kind of like to make the arrows look kind of nice, whatever. That looks pretty good. Now let's look at what it did for some of these. So we can look at the object window for ore processing capacity, and it represents our choice regarding the scale of the operation. So we get to choose how big we're going to make the mine. Its units are an MT per year. MT is millions of metric tons, I think, per year. And as we saw, I didn't fill in the definition yet. And from the capacity, that determines what our capital investment is going to be. Upfront investment to set up initial mining operations, and that's in dollars. Then that determines a debt service payment. Operating expenses is determined by how big the mine is. And the amount of lithium produced is determined by how big the mine is, and also the recovery rate and the ore purity. So what is recovery rate? The percentage of lithium in the ore that gets extracted by the DLE process. Okay, that's in ton LCE. Ton with an E, NE means metric tons, right? LCE is lithium carbonate equivalent. So it's the amount of tons of lithium that gets extracted for each ton of ore that's processed. Okay, and ore purity is what? The amount of lithium by mass in each unit of raw ore material. So that's the amount of lithium that's present. So I guess we're going to extract some fraction of that via the recovery rate. Okay, I get it. And then revenue is based on lithium produced and market price, and expenses and revenue or profit. Okay, so that seems like a pretty good starting point. So it said now we should populate the definitions. Why don't we just ask it to do it? So I'm just going to say, can you populate the definitions for all of these? And it suggested using a low-end scale mining operation, which sounds like a good idea since we're probably going to want to start low scale and then scale up as we adopt future technologies. So that makes sense. So I'm just going to say, okay, so watch the nodes in the diagram. If it defines them, the cross-hatching should go away. Okay, some of the cross-hatching went away. Actually, all the cross-hatching went away. It looks like it finished. Certainly, let's go ahead and set the definitions for these variables. Update the definitions for each variable with the values provided. I'll proceed to make these updates. I've populated the definitions, okay, and it showed us what the definitions are there. Let's go ahead and look at the variables, or processing capacity, it set it to 1 megaton per year. So that must be what a low-scale operation would be. 1,000,000 tons per year. I don't actually work in the mining industry, so I don't know if that's low scale or not. Probably is. Capital investment. So that's okay. So it set it to $50 million times the ore processing capacity. So the more capacity we decide, the larger we decide to make the mine, the more capital investment we need. And it looks like it's set that to be something that scales linearly. Operating expenses. Okay, same idea. The more capacity, the bigger the mine, the more operating expenses we have. And looks like that's 40 million a year. And then the lithium produced is the ore processing capacity times 1 million times the recovery rate. Interesting. So I see it left off ore purity there, but it left the arrow in there. So I think that's an error. I think it needs to have ore purity. So we'll fix that. So notice, that it does make mistakes sometimes. And anything else interesting? Let's see what it actually did for recovery rate. Okay, it used a probability distribution, uncertain, low, medium, high. So this uses a 10, 50, 90 estimate of the recovery rate. So it's estimating a median of 70% that will recover 70% of the lithium, but it's not certain. It's somewhere between 65, 75. That's the 10 and 90th percentiles. And LB means it's always a positive number. And ore purity also used a distribution. This is so it's saying the rock that we mine has about 1% lithium in it, but it might be as low as 0.5 and as high as 2%. That's 10, 50, 90. And what's the market price? It also used a probability distribution there. Market price, the median is like $35,000 per metric ton of LCE. And maybe as low as 25 and as high as 60. All right. Revenue. Let's just look at these, see if it has any other mistakes. That seems to make perfect sense. It's the market price times the amount we produce. Profit is revenue minus expenses. Okay, that's great. Debt service payment. This is the annual payment on the financing for capital investment. Okay, so PMT is the amount you pay on a loan. So this is like assuming we're going to be paying 8% interest for 10 years on the capital investment loan. And, okay. And so the minus there, I'm going to evaluate this for a second. It's a positive number. Just the convention with PMT is you need to put a minus in front. And expenses is operating expenses plus debt service payment. Okay, cool. All right, so that all looks good. Now, since everything is defined, we can actually evaluate all of these nodes. So let's look at the result for profit. This is the mid value. This is ignoring uncertainty and just using the median value for the uncertain estimates. So we can switch that to be the mean value based on the uncertainty distributions. And it's saying, we can expect about a $275 million profit per year. We can also look at the full distribution, and I like the exceedance probability curve. Let's zoom in a little bit here. Okay, so this is showing the probability that the profit will exceed a given number. So it's almost certain that we're going to have a positive profit, and there's about a 50% probability that the profit will exceed $200 million. 10% probability it'll exceed $560 million. So that's the probability distribution. The actual profit is uncertain. We could look at the amount of lithium produced. We could also look at its exceedance plot. Okay, and we see that a mean of 7,000 metric tons per year, 90% probability we might actually exceed 15,000 metric tons a year. So that's our beginning thing. So I think this did a really good job at an initial starting point. It doesn't actually incorporate the main thing we care about yet, right? Which is how to adopt the new technology over time. So the next thing we need to do is to really add in a time dimension to this model. And so a good place would be with cash flow. So I'm going to say, please add a cash flow variable with time going from 2025 to 2050. And then let's add a net present value as another objective. Okay. I expect to see some new nodes appear. Okay, and several variables appeared with some arrows, and they're all defined. So once again, it's up to me to rearrange this a little bit. So I'm going to just kind of move this stuff down a little, and actually, why don't we do it this way? Put that there, move this here, move this here, cash flow, and put the objective out here on the right, and discount rate can go above it. Okay, so it added a discount rate as well. Okay, so discount rate is 10%, and okay, so what is this investments? And it added a new investments variable. Let's look at that. Annual investments in the mining operation, indexed by time. So it looks like for the very first time point, it's using capital investment and 0 everywhere else. Okay, so what it's done there is it's added in a time dimension. So recall that our capital investment was 50 million. So here it added it in with a time dimension. And then over here on cash flow, it used the negative investments. So that has the time dimension, and then revenue minus added revenue minus expenses. So okay, so that's cash flow, and should be able to evaluate that. Again, that's the mid value that ignores uncertainty. So we could look at the mean value, and we can see that it is a little less in the first year. We could graph that, and we could even look at the probability bands. Okay, these are the range of cash flow in each year. Okay, so that now we have the time dimension. Okay, it seems like it gets a little harder from here. So what we want to actually look at upgrading the DLE technology. So let's do that in a new module, because we're getting a lot of nodes here. Okay, so I'm going to just say planning of DLE upgrades. And I'm going to open that. Let me open that module and put a description in there. So this module forecasts improvements in the state of the art of DLE. I'll put my name in there. All right, and we'll open its diagram window here, make it a little narrower. Okay, so we'll put the new variables in here. So I want to create a decision variable for when we should upgrade our DLE. So I'm going to say create a decision variable upgrade process as a table of checkboxes indexed by time, and a new scenario index with, say, baseline and biannual upgrade in scenarios. Okay, so make it capital. So I'll use this to specify possible. I think it might be good just to tell it. I'll use this to specify possible schedules for upgrading to the newest state-of-the-art DLE technology. Go. So hopefully we're going to see a decision variable appear, maybe an index for scenarios. Good. I see them appear. Nice. It says, I have created the scenario index with 2 scenarios, baseline and biannual upgrades. And the upgrade process decision variable is a table of checkboxes indexed by time and scenario. Now you can use this to specify possible schedules. I'll show the edit table for upgrade process now. I don't see any edit table being shown, but let's look at these ourselves. So for scenario, I do see the 2 options for scenario. It didn't actually fill in a description. And for the upgrade process, it's an edit table, and it says year where mine adopts the newest state-of-the-art technology. And we can open the edit table, and it is a table of checkboxes. That's awesome. Okay, and so for baseline, let's say we don't ever upgrade, but for biannual updates, let's upgrade every other year. So the first year will be our starting technology, and then on the second year, we will upgrade like that. Okay, we could add more scenarios now with that structure, but let's just start with those. Now we want to use that to decide when to upgrade, and so we're going to need a few things. So let's go over here and let's focus on recovery rate. So each time we upgrade the DLE technology to a newer state-of-the-art, let's imagine the recovery rate improves. Okay, so I'm going to make an alias of recovery rate. Okay, move it into this module. And actually, you know what? We need recovery rate to vary with time. So actually, maybe what I'm going to do, let me back up on that. I'm going to change this to be initial recovery rate. Okay. I'm going to add another variable here called recovery rate, have the original name, and I'm going to switch this guy to use recovery rate. So recovery rate will vary with time, and we'll go like this. I can maybe switch these to so the arrows don't cross. Okay, let me just tell it what I have in mind here. I can just copy this. Okay, so here, okay, so we're going to have that one just be the recovery rate when the mine opens, and this one is going to be which changes over time as new DLE technologies are adopted. Okay, so let's make aliases of these and move them into the module. So it'll kind of focus attention on these, which I think we'll need. And we're going to want recovery rate to change each time we upgrade the process. Now we're going to also have to track how the state-of-the-art technology improves, even if we don't adopt it, right? So that's like continuously improving. Okay, so maybe I'll just have it do that. So now I want to forecast the future state-of-the-art recovery rate. I expect the state-of-the-art to improve stochastically at around 6% a year, give or take 2%. And with the rate asymptoting to 100%. So it can't go above 100%, right? And then we'll need, we'll need a recovery rate to adopt the state-of-the-art value in any year that I've selected to upgrade the process, right? Okay, hope that's clear. Let's see what it can do with that. So if it succeeds, it ought to add a couple new variables. Ooh, good. Nice, nice. Rate of improvement and recovery rate. State-of-the-art recovery rate. Perfect. Okay, that looks great. Actions. Okay. It created them. All right, so let's first just see what its response was here. Here's how we can forecast the future state-of-the-art for recovery rate and upgrade the recovery rate variable. Create a chance variable for the state-of-the-art rate of improvement. Create a variable for the state-of-the-art recovery rate, which improves stochastically over time. Upgrade recovery rate variable to adopt the state-of-the-art recovery rate in any year designated by the upgrade process variable. I'll proceed by creating these variables and upgrading the recovery rate definition. So actions, create these variables, and update recovery rate. So definitions. Okay, so here, let me rearrange the nodes a little bit. Let me rearrange these nodes a little. Let's just see what it really did. State-of-the-art rate of improvement. Okay, so it's saying the rate of improvement is about 6%, give or take 2%. That's the standard deviation. And it's independently sampled over each time period. So that's the stochastic part. It's a normal distribution. State-of-the-art recovery rate used a dynamic. So what this says is let me just put this on a separate line. I'll indent it. Yeah. So what this says is in the first year, it's the state-of-the-art recovery rate is the initial recovery rate. So we're starting out with the technology in that year. And then here it's doing something, it looks like it might be incorporating an asymptote using the previous value. So it's going to increase by the rate of improvement, and it's kind of hard to interpret that. It looks like it's incorporating an asymptoting relationship. So let's just see. And yeah, that looks awesome. See how it improves, but it asymptotes to 100%. Out here in 2050, it gets up to 94%. If we look at the probability bands, we can kind of see the range of uncertainty. So we start out with a range of uncertainty, and actually they kind of narrow as it goes up. Okay, that looks awesome. And recovery rate is now the actual recovery rate. Okay, so once again, it's using this dynamic. It says in the first year, the recovery rate is the initial recovery rate. And then in each subsequent year, if we upgrade, then it's going to be the state-of-the-art recovery rate in that year. Otherwise, it's going to be the previous one. It's going to remain unchanged. Okay, that looks pretty nice. I'm just going to evaluate recovery rate. So let's graph it. I'll do mean here. And so if the red line is the baseline where we never upgrade the technology and it just stays at 0.7, mean of 0.7, and we can see every other year it takes a little step up with the biannual upgrades, improves every other year. So what's the impact on that, on, say, profit? Or net present value. We haven't incorporated any cost to upgrading, so it can only be good, right? It's got to improve profit. So let's make the key of this the scenario, and let's go to the last year. And of course, we can see that the biannual upgrades has a higher profit than the baseline does, as expected, because there's no cost involved. Okay, so next thing is we want to actually incorporate the cost of upgrading as well. That's key. So this is getting a little bit crowded, this influence diagram. So I'm going to take the stuff at the top here all has to do, let's say, with financing. So let's make a module called financing. And let's move all those into that. I'm just going to keep a copy of investments here, make alias, and I'll take these top nodes and one copy of capital investment, and I'll move those into financing. Looks a little easier. And then we'll go into financing, and we'll incorporate the cost here. As we incorporate the cost, though, we're going to want to use upgrade process. So I'm going to just also make an alias of this and move it in there. Now, kind of having things that are relevant to what you're working on in the same module, that's good in that you're telling a story and all the pieces for that story are in one place. But it also helps the assistant because you're kind of telling it, hey, I'm in this module, I'm looking at this module. It knows what you're looking at when you ask it a question, and it sees, the arrows, it sees the variables in that module, and that can kind of help it figure out also what it might do. We're going to have let's hit a wrong button. So DLE upgrade cost, change its identifier. So this is the capital cost to upgrade operations to the newest state-of-the-art DLE technology. Right? We want this cost to be put into investments in the year that we upgrade. Let's see, debt service payment. Recall that this is, okay, 8%, 10%. Just to make it a little cleaner, I'm going to move these into their own variables, okay? And let's see, this is in years, okay? So the okay, number of years for the loan for each capital cost borrowed, if that makes sense. I don't know, kind of weird. This will be kind of obvious by the name, but whatever. Okay, and so what we're going to do here is I'm just going to replace these with the actual things. It just seems a little cleaner. Okay. And this has to be updated somehow because that's a little too simple. So, okay, a few things that need to be done there. I'm kind of getting confused. So let me just say, can you incorporate the DLE upgrade costs for the years we choose to upgrade? Okay, to incorporate the DLE upgrade costs for the years that you chose to upgrade, I will add the capital cost for upgrading operations to the newest state-of-the-art DLE technology in the investments variable. Let's start by looking at that. Ooh, okay. That's got a bit more complex. I'm going to put a new line there. Okay, so it's saying in the first year, it's going to be indexed by time. The initial investment is capital investment, and then upgrade costs is going to be the upgrade costs in the years that we upgrade the process and zero otherwise. And then the result of this will be these two added together. That, I think, makes sense. Let's just see what it got. Okay, something has not been explicitly defined yet. Okay, so it hasn't explicitly defined DLE upgrade cost. All right, so let's just say this. Let's say the upgrade cost is 50% of 50% of the capital investment. Can we untangle some of the arrows here? Yeah. Okay, about like that. Okay, so let's look at the investments here. All right, I'm going to pivot. And what we're seeing here is in the baseline, there's just the $50 million capital cost in the first year. And in our biannual, we invest $25 million every other year in upgrade costs. That seems good. Cash flow. So this right here is going to have to change a little bit, right? Because debt service payment is saying it's only doing the debt service payment on the initial loan, not on every investment we make. Also, this is going to be just a single number. And we actually want this to basically not have any payment until we take the loan, and then only have payments for like the next 10 years after that. Okay, so if we change this guy to be investments, then now we have a time index, but we're only getting the investment. This is what the payment is for the loan that was taken in 2027. This is what the payment is for the loan that was taken in 2029. But we need that payment to occur for like 10 years for the loan in 2029. Let's see if I can just kind of explain that to it and see if it can upgrade it. It seems like this can be a really tough definition to get right. But let me kind of explain what I want. So, by the way, it knows what I'm looking at, right? So I was looking at debt service payment. I could even, even have its object window open if I wanted it. So it's really clear I'm looking at it. So that's why I say this variable. Okay, this variable currently shows the annual payment on the investment made in each year, but that does not account for the starting year of the investment, when the loan starts, nor the fact that the payments stop after loan duration has elapsed. It needs to also sum up payment for each investment. Okay, so for example, if we invested $2 million in 2027 and $5 million in 2029, then the payment in 2027 and 2028 would include only the payment on the $2 million. And in 2029 and 2030 and so on, it's going to be the sum of both payments. But then after 2037, after the loan duration is expired, it should stop including the payment on the $2 million. I don't know. Do you understand what I'm trying to say? What I am explaining? I guess we'll see if I've been clear. It changed the definition. It says, to correctly model debt service payments, accounting for the starting year of each loan and the stopping of payments after the loan's duration, we can use cumulative debt payments. The new definition should sum up payment for each investment and also consider the years where the payments stop and start. Okay, so let's look at this definition a little bit in detail. Okay, so payment for loan, that's what we had before. That's the amount of the payment for the given loan. And then it creates an index D that goes basically from 0, the starting year, to loan duration -1. And it reindexes that payment across that. So that will add in a dimension. And then it sums over that dimension. One mistake there. In Analytica, when you sum, you need to tell it what index to sum over. Let's just see here. All right, so in the baseline, our loan goes for 10 years. That's what we expected. We can see here it goes for, then the next loan kicks in and the payment goes up a little. The next loan kicks in, it goes up a little bit more. And then here, the first loan expires and the next one kicks in. Here, I guess they're expiring and kicking in at the same time. So then it becomes kind of constant. Okay, so that seems possible. So that's what our loan payments look like. Okay. Wow. I think we have that one. Okay. This is our financing. I'm missing expenses and revenue. So I think I should probably take these two and I'll make aliases of them and move them into that node to highlight. Okay, and just so I can see it all. Okay, so we have now incorporated the upgrade of DLE technology into both the recovery rate and a cost for upgrading. So we basically have a trade-off in there. I think we would also expect it to lower certain operating expenses, but I'm not going to go into that now because I think we've covered a lot of the essence of things. So here's our net present value, expected net present value, and we can see for each of these scenarios, the biannual upgrades is coming out a little bit better than the baseline. And if we want to add another scenario, we could do that. How about annual upgrades? Okay, so we're gonna upgrade every year. I mean, not really the first. I guess it doesn't matter if we check it or not. Okay, so biannual upgrades is a little bit better than annual upgrades. All right, so that is a good place to stop with the demo portion. Okay, so back to the slides. So how does Assista do all that? Well, there's a lot going on behind the scenes, and I'm not going to dive in too deeply. The main point here is that it's not just a chat bot with some retrieval augmented generation. When you ask a question, it starts out calling GPT with this prompt. Here's what the user just asked. Do not answer it. Instead, analyze the question. Figure out what type of question is being asked and what extra information would be useful. If it responds saying that the user is asking it to structure an influence diagram, which is something likely to require many conversational steps, then the next thing it does is to construct a discourse plan. For my example, step 1, make sure I have enough information about the real-world situation, and if not, ask clarifying questions before proceeding. Step 2, scope the problem, and so on. Then, based on the information from the analysis and where we are in the current plan, it customizes the prompt that it'll use when it asks GPT in another call to answer the question. Before asking for that response, it collects reference materials that seem relevant, information from within your model that appears relevant, and information about what you're looking at in the UI. It supplies these along with the tailored prompt, the chat history, and the user's current question when it asks GPT for the actual response and the actions to execute. And that's just one pathway it might take, depending on the initial analysis. The main point is that an AI assistant involves more than just a chat GPT interface to a large language model. I'd like to conclude today by looking at the synergies between AI and model-based decision-making. I entered the field of machine learning as a graduate student 37 years ago, in 1987, and as I've seen AI progress, especially in the past 5 to 7 years, I've often pondered whether AI is about to make model building and risk analysis as we know it obsolete. What happens when we have an AI technology that can just do the entire analysis for us? My conclusion is that even in that future, and in fact especially in that future, explicit decision models are really important. I mean, do you trust every analysis you encounter? When you see the results of an analysis of something, do you interpret it as the entire picture, something to be followed with blind trust? How do you know when someone's recommendations should be trusted, whether it's from a human or an AI? As AIs of the future make inferences with more and more complexity, explicit decision models may hold the key to enable us to understand, interpret, and trust the conclusions and the recommendations. A good decision model is visual and transparent, allowing our feeble minds to understand what it's doing and what factors it incorporates. It's interactive, so we can explore many variations. We can progressively extend and adapt a model over time. And because a model embodies the rationale behind our decisions, we don't have to wonder whether the best actions have been hallucinated. I also think model building will fundamentally be a collaboration between humans and AI assistants. The collaboration is how we ensure that we're on the same page. AI assistants will help us build decision models better, faster, and easier, requiring less specialized expertise, and that makes model-based decision-making, and hence better decision-making and risk management, more accessible to more people. Thank you.